Hello everyone, you're welcome back to Stress Arena Academy. In my today's video, I'm going to be sharing with you my knowledge on chemical bonding and how how question is being set on this topic in JAM altogether. So if you're here, then you're writing JAM next year 2023, you are in the right place to learn. Here, I'm going to be helping you with my past questions, whereby I'm going to be sharing knowledge on the questions that have been said so far on this topic in JAM and what you need to understand under this topic, so that next year's JAM will be very easier for you to ache 300 plus. Thank you so much. If you are new to my channel, don't forget to subscribe to my channel. Click on the subscribe button, the like button, and then share my video with your friend. And don't forget to drop a comment for me, because your comment means a lot to me. Thank you so much. Now let's start with this. Now, before I start today's class, my first question I'll be asking is, why is it that chemical substances undergo chemical bonding? There is a reason why many substances undergo chemical bonding. Without wasting much of our time, one of the major reasons why they undergo chemical bonding is for them to attain the structure of inert gases. Now, what do you mean by inert gas? In the periodic table, there are some elements, there are some groups of elements in the periodic table in which they never undergo any kind of chemical reaction. Now, one of the major reasons why they don't undergo chemical reaction is because they have a complete octet or duplex structure. What do you mean by octet structure? Let me try to write electronic configuration for you. Now, take a look at something. In electronic configuration, we believe that s orbital can only occupy 2 electrons, p orbital can occupy 6 electrons, d orbital can occupy 10 electrons, and f orbital can occupy 14 electrons. Now, for the first 20 elements, let me say we are considering only s and p orbital for the first 20 elements. So when we said octet, if an element has a complete p electron to be 6 and a complete s electron to be 2, if I combine these two together, because sp and sp orbital makes up a single shell, which is your m shell, which is my n shell altogether. So this shows that any element that has a complete n shell, that means to have 8 electrons, we say that element has a complete octet configuration. And one thing about this is that element that has a complete structure of 8 electrons is more stable than any other element in the periodic table. So because of this kind of issue, many elements want to attain this same structure of the noble gases. So they can only attain the structure of the noble gases only in one way, by combining with each other. And that combination might be done either by losing or gaining electron, or by sharing electron with themselves or their neighbor altogether. Now, that's what brings us to what we call chemical bonding altogether. So chemical bonding is the loss, it is the sharing of electron, or the transfer of electron from one atom to another atom. That is what we call chemical bonding. Now, I would like you to understand something in this place today. What is the major thing that we need to know for we to pass our JAM without wasting much of our time? Now, the types of bonding that we need to know here, we have chemical bonding is classified into 2. We'll be talking about the interatomic bonding, and also what we call the intermolecular bonding. Another name given to this is known as intramolecular bonding altogether. So in a nutshell, interatomic bonding simply means the bonding that exists between 2 atoms altogether. It is a kind of bond that exists between 2 atoms. Let's say, for example, for H2 hydrogen gas to be formed, hydrogen will need to join with another hydrogen to form hydrogen molecule. Are you getting hydrogen gas molecule? Now, there is a bond that is holding this hydrogen atom to another hydrogen atom. This bond holding them together, that's what we call interatomic, bond between 2 atoms altogether. Now, but when we talk about intermolecular bonding, please get a pen and note all this. When we talk about intermolecular bonding is a bond that exists between 2 molecules. Let's say, for instance, you don't know that hydrogen molecule is the form. This is just ordinary molecule, and don't forget that when molecule combines to another molecule, it forms a substance, which is matter. altogether. So there is a bond that is holding this hydrogen molecule to another hydrogen molecule, which can also hold it to another what? Hydrogen molecule. This kind of bond that is joining molecule to another molecule is what we call intermolecular bonding. That is number 1 point I want you to know. The second point I want you to know in this place is that these two types of bonding determine the properties of the what? Substance. Now, the interatomic bonding is used to determine the chemical property of the substance, while the intermolecular bonding is used to determine the physical property of the substance. Now, talking about the physical property of the substance, we are talking about the solubility of the substance, the viscosity of the substance, the melting of the substance, the melting point, the boiling point of the substance. So this is what you need to know. And the lights, they are more than that. Altogether, I think I've been able to make sense with what kind of property that determine physical and chemical property altogether. Now let's jump into what? Interatomic bonding. What are the types of interatomic bonding that we have, and what do you need to know about this type of interatomic bonding? Then I move to intermolecular bonding as well. Now, and what you need to know to pass your jam about that. Now, for interatomic bonding are just only 4 types. We have 4 types of interatomic bonding. The first one is what we call the electrovalent bonding. The second one is what we call the covalent bonding. The third one is what we call the coordinate covalent bonding. Another name given to this, you call it the dative bonding. Altogether, now the fourth one is what we call the metallic bonding. Now, this bonding are known as interatomic bonding. Now, let me take them one after the other, and then let's see how this bonding is being formulated. I want you to take note of this. Before I start the explanation of this, I'll be giving you some tip on what's formed bond. Now, the major reason why bonding is always formed when there is a difference in electronegativity. Are you getting what I'm saying now? One of the major things that determine the bonding in which an atom will undergo is the difference in electronegativity. You know, when we talk about electronegativity, we said it is the measure of the ability of a substance altogether to attract a shared electron towards itself in a molecule. That's what we call electronegativity. And this electronegativity can be used to determine any kinds of bond that a substance can undergo. Now, take note on this electronegativity. Now, if the electronegativity difference, what is my electronegativity difference? Let me show you something. If you are moving across the period in the periodic table, let me say I have group 7 elements, group 6 elements here. Now, this group 6 elements, let me say oxygen, I have fluorine here. Now, electronegativity increases across the period as I'm moving from left to right. It simply shows that fluorine is the most highly electronegative element that is found on Earth. Next, we can have any other element that is found below it here. So fluorine is the most highly electronegative element. Are you getting something now? We have oxygen is lesser, has lesser electronegativity than what? Fluorine. But the problem that is here that I want you to show is that these two elements are very, very close to each other, which showcase that the electronegativity difference, you know, this one has zone electronegative value, this one has zone electronegative value, but there is a difference there, the difference in the electronegative value. If these two elements are meant to combine with each other, the kind of bonding that they are going to form depends on the difference in the electronegative value. But because these two elements are very close, they will have a lesser difference in electronegative value, which is even less than 0.5 altogether. So they have a less difference in electronegative value. But if you consider the group 1 elements and the group 2 elements, now the distance between the group 1 element and the group 7 element is very, very far, which showcases that they have a larger difference in electronegative value. This difference in electronegative value determines the polarity of the substance. Polarity of the substance. The word polarity simply means the production of positive and negative charge in the two ends of the substance. For example, now, if I have water is the formation of hydrogen and formulate water. Now, these are the two ends, hydrogen and oxygen end. This end is having a partial negative charge. This one is having a partial positive charge, which makes this molecule to be polar. Polar simply means it has one side to be positive and one side to be what? Negative. Now, let's take a look at how this thing affects, and I will show you a question that is asked on this in JAM, where I'm going. Now, number one, electronegative value. How does it determine the bond? Take note of this. Now, if the difference in electronegativity, let me say change in electronegativity of a substance is, if the change in electronegativity of a substance is greater than or equals to 0.7, then that substance, the kind of bond that substance will undergo is what we call electrovalent bond. That substance will have what we call an electrovalent bond. Altogether. Now, number two, if the change in electronegativity value is less than 0.5, the bond is going to have equivalent bond. Equivalent bond. But what kind of covalent bond? The bond is going to have a polar covalent bond. Now, the third one is now, if the change in electronegativity value is equal to 0, then the bond will be a non-polar covalent bond. Now, these are the these things I need to note. Now, let me now take you through all this. How does electronegativity affect polarity of a substance? Sorry, how does electronegativity affect what? Polarity of a bond? Before I now move on to the main bond itself. We've known this. Now, how does electronegativity value affect the polarity of the bond? Now, the greater the electronegativity value, take note of this. The greater the electronegativity value, the greater the polarity of the bond. When the electronegativity value is great, then the polarity becomes what? Greater. But when the electronegativity value is less, the polarity becomes less. Let me write it like this. Now, the higher the electronegativity value, the more the polarity of the bond, and vice versa. I want to get out like that. So that's what we are trying to see here. That when the electronegativity value is great, then the bond is what? Electrovalent. And don't forget that what? Ionic bond is the bond with the greatest polarity. So when the electronegativity value is greater, the bonding tends to be what? Having a greater polarity. When the electronegativity value is less, I get you now. It has a polar covalent, but when it is equal to 0, we have a non-polar covalent bond. Now, before I move on with this, let me just check a question on JAM that asks question about this electronegativity value. I think I have a question here which says, I'm trying to use this JAM past question, JAM series remains for what? My explanation. Now, let me take a look at this. Okay, I think I saw a question. Okay, take a look at this. They said, as the difference in electronegativity between bonded atom increases, as the difference in electronegativity between bonded atom increases, polarity of the bond dash. Now, according to my explanation, if the difference in electronegativity between bonded atom increases, then the polarity will also increase. Option A, we have polarity will decrease, B, increase, C, remain unchanged, and then option D, the polarity reduced to 0. What is the answer? Our answer should be, as the difference in electronegativity value increase, the polarity of the bond will also what? Increase. So when the difference in electronegativity value decrease, the polarity of the bond will what? Decrease. I think I saw another question about that, which they asked in JAM. Okay, they said, the greater the difference in electronegativity between bonded atom, the A, lower the polarity of the bond, B, higher the polarity of the bond, C, weaker the bond, E, higher the possibility of the substance form being a molecule. Altogether. Now, take note, if the polarity of the bond is even greater, the substance will not form a molecule again, it will become a formula unit. Take note of that. So our answer to this is that what? When the difference in electronegativity value become increased, then the higher the polarity of the bond. I think I've been able to make sense about this electronegativity and polarity of the bond. Let's continue with my explanation. Thanks. Now, I'm coming back to what we call what? Example of substance that is non-polar covalent and the substance that is a polar covalent bond, that has a polar covalent bond. Yeah, okay. I think we have electrovalent bond. When we talk about electrovalent, or another name given to it is ionic bond. Ionic bond involves the transfer of electron between a metal and a non-metal, which involves simply means what? It is the gaining or the loss of electron between a metal and a non-metal. Now, which substance is going to lose electron and which substance is going to gain electron, and what is the main question that you should be expecting on this in JAM? That's what I want you to know. Now, take note of this. Now, electrovalent bond always occur between a metal that is found in group 1 and group 2, and also between non-metals in group 6 and group 7. That is where majorly electrovalent bonding occur. Now, you see, metals want to be stable and non-metals want to also be stable. And they can only achieve this their stability either by losing electron or by gaining electron. So one substance will lose and the other substance is going to gain the electron. Altogether will be like that. So in this case here, metals are meant to what? They are known as electron donor, while non-metals are known as electron acceptors. Altogether. Now if you take a look at the electronic configuration of metal, let me take an instance. Let me take sodium an instance. Sodium has 1s2, 2s2, 2p, 2p6 and 3x1. Sodium has an excessive electron in its s orbital. You know, this is complete, but because s orbital can, the third shell here should occupy 8 electrons in total. Should occupy what? 8 electrons, but out of the 8 electrons, the third shell, which is shell 3, is only having 1 of the electrons. That means there is still need to get 7 electrons to complete this what? Octet structure here. But rather than for sodium to what? Accept 7 electrons, there is no any element that will donate 7 electrons to sodium. What will sodium do? Sodium will rather donate this 1 electron that is stopping it to become stable, and then to be left with only electron in the first and the second shell altogether. So sodium will be serving as a what? As a donor. It can easily donate this 1 electron to any atom that needs the 1 electron. Altogether like that. So for sodium to undergo bonding, let me say I have what? 281. This is sodium. If sodium is to react with chlorine, for instance, or fluorine, for instance, fluorine is 2 and 7. Now, fluorine also needs 1 electron to complete its octet structure, and sodium has 1 electron. What will happen? Sodium is going to donate 1 electron to fluorine, while fluorine is serving as an acceptor of the electron. Altogether. So when sodium donates 1 electron, it becomes sodium ion with only 2 and 8 electronic configuration. While if fluorine accepts electron, it becomes fluoride ion with only 2 also and what? 8 electron. Are you getting what I'm saying now? Now we can easily say that in this place here, okay, so we can easily say that in this place here, sodium ion and fluoride ion are isoelectronic. Isoelectronic. What do you mean by that? Simply means sodium ion and fluoride ion have the same electronic configuration, and this their electronic configuration is the same as that of the noble gases, which is neon. Neon also have 2 and 8 electronic configuration. So sodium ion and fluoride ion is isoelectronic with neon. They have the same electronic configuration with neon. I think I'm able to clarify that. So what is the major thing I need to know about electrovalent bonding? Now, it's one of the property. Let's take a look at the property of this bond, this electrovalent bond, before we move on to covalent bond. So please take note, I said it can occur between metals and non-metals. So you can what? Find your solution to that. Now, what is the property that you need to know about this kind of bonding that is here? Number 1, the property is that electrovalent bond altogether, a substance with an electrovalent bond, are you getting something now? Has high solubility. So no let me use that. A compound with an electrovalent bond is soluble in polar solvents. Is soluble in what? Polar solvents. Example of polar solvent is water. They can only be soluble in what? Polar solvent, but insoluble in a non-polar solvent. They are soluble in polar solvent and insoluble in a non-polar solvent. Non-polar solvent like benzene, toluene and the likes, they are non-polar solvent. Or I think methanol. Methanol is also a non-polar solvent. So any substance that contains electrovalent bond will not be soluble in benzene and methanol, but they can be soluble in water. That is number one. Number two is that the reaction between them is very, very fast. The reaction of what the reaction between a compound that has an electrovalent bond is very fast. So simply means they have a fast reaction. They have a what? Fast reaction. I want you to take note of that. Number three is that any substance that has an electrovalent bond in it, like example of this substance is sodium chloride, sodium fluoride, I think we have calcium chloride, magnesium oxide, all these substances here, they have what called electrovalent bond in them. Now, and one thing about them is that they possess these properties, these physical properties. They possess these properties altogether. So, a substance that has this kind of this thing possesses this property, both physical and chemical property. Now, take note, let's say they have fast reaction. Their reaction is very, very fast. Number three is that they are soluble in polar solvents. They have a fast reaction. Then they conduct electricity in molten and aqueous form only. They conduct electricity in molten and aqueous form only. Now, simply means they can only conduct electricity when they are in solution. They don't conduct electricity when they are not in solution. Like for example now, if they are in solid, because they are solid, majorly any substance that has electrovalent bond in them can either be a solid or a liquid. They can never be a gas. They are either a solid or a liquid. Are you getting what I'm saying now? So they are solid with high melting points and liquid with high boiling points. That is one thing about them. They are solid with high melting points and liquid with what? High boiling points. That is number 4. They are solid with high melting points, high melting, and liquid with high boiling points. All together. Now, this is the major property of this element. These are the major 4 properties that this element usually possess. 1, they are soluble in polar solvents. They have fast reaction. They conduct electricity in molten and aqueous form. But when they are in solid form, they don't conduct electricity in solid form. Why? Because they are in solid form. Their ions are arranged in a crystal lattice form. Are you getting me? They are arranged in a crystal lattice form. So because of that, they don't conduct electricity in solid form, except when they dissolve in an aqueous solution. That's when they are in molten solution. That they conduct electricity. I think I've been able to grab our attention to this. Now, what is the question that is being set under this electrovalent bond only in JAM? Let's take a look at this question that is here. I think I have a question. Okay, look at this question. It said, which of the following statements is true? When the potassium atom forms its ion. When potassium atom forms its ion. Don't forget that I said, when any of these metals in group 1, when they lost electron, they form their ion. Now, what should we expect about that? So when potassium is found in group 1, when potassium atom or sodium atom or calcium atom, when they form their ion, what should we expect? Let's take a look at the option. Option A, it gains 1 electron and becomes neutral. Option B, its atomic number decreases. Option C, it achieves electronic configuration of argon. Option D, it loses 1 proton. Option E, it loses 1 neutron. Let me analyze this option for you one after the other so that you can understand what to pick. I'm sure that some people already knew the answer to this. Now, let's take a look at this. When potassium atom loses electron, potassium should have this 2881. This is the neutral potassium atom. because it has an atomic number of 19. Atomic number of potassium is 19, K19. Now take note about this. The atomic number of an element is the same thing as the number of protons in that element. Altogether, so for an atom to be neutral, the number of proton must be equal to the number of electrons. So in a neutral potassium, number of proton is 19, number of electron is 19. But please take note of this. Number of proton does not change, but the number of electron can change by either losing electron or gaining electron or sharing electron. They can change number of electron. Now, a neutral potassium has this. When potassium become potassium ion, it loses one of its electrons to form potassium plus potassium formulation, which is what? 288. Now, what do you need to understand about this? One thing I need to understand about this is that what? The neutron of potassium remain the same, because there is no business with what? Electron does not have any business with neutron. One, the neutron of potassium remain the same, and the atomic number of potassium remain the same as what? 19. The only thing that changes here is the number of electrons as changes from 19 to 18. It simply shows that what? When potassium loses electrons to become potassium ion, there is a reduction in electron. So electron has been reduced to 18, but the number of protons remain the same. All together. Now, the next thing I want you to take note about that is that it is going to majorly all atom losses or gain electron to obtain the stability of the nearest noble gas. So the nearest noble gas to potassium is argon. Argon is having an electronic configuration of 18. So when potassium loses electron, it has the same electronic configuration of what? Argon, which is 288. So in this case here, it has the same structure, the same what? It is isoelectronic with argon. Isoelectronic. When we say something is isoelectronic, simply means it has the same electronic configuration with argon. So potassium ion and argon are what? Isoelectronic. Now, let's now pick answer to our question. They said, which of the following statement is true when the potassium atom forms its ion? A. It gains one electron and becomes neutral. An atom will never gain an electron to become neutral. An atom can gain electron to what? To become ion. And in this case here, it's only lost electrons, so option A is ruled out. Option B, its atomic number decreases. I have explained that atomic number remains the same because it's the number of protons, but it's only the electron that will decrease. Option C, it achieves electronic configuration of argon. Yeah, it is going to achieve the electronic configuration of argon, which is the correct option in that question. Are we together with me like that? Now, that's that for that. I think we can move on. Okay, I said another question. I said, which of the following is not true of electrovalent compound? Which of the following is not true of electrovalent compound? A, they are solid. All electrovalent compounds can either be a solid or liquid, which is true. All together. Option B, they do not vaporize easily. Option C, they usually dissolve in water. All electrovalent compound will what? Dissolve in water. I want you to note that. Option D, the element forming the compound normally have their valence electron in shared state. So the element forming the compound normally have their valence electron in shared state. No. This is what they mean by that. Sharing of valence electron is only done by covalent, a substance that is having a covalent bond. But a substance that has electrovalent bond only their valence electron can only be what? Transferred from one point to what? Another. Option D is right out. Option E, they conduct electricity, which is correct. Option B is also correct. They do not vaporize. They don't really what? Vaporize easily. They don't turn to vapor easily. Are you getting something now? They are solid that does not turn to vapor easily. Why? Because of the what? High melting points that they have. They have high melting points and high boiling points of, if they are liquid has high boiling points, and their solid has high melting points. So it makes them not to vaporize easily. A substance that can easily vaporize will have what? A low melting point. So it can easily become a vapor. So the correct answer to that question is option D. The element forming the compound normally have their valence electron in shared state, which is wrong. Are we together with that? Now, let's now move on to this without wasting much of my time. Covalent bond. Now, what you need to know about covalent bond, I think this one is kind of what? Kind of much, but let's take a look at it. Covalent bond. What do you need to understand about this covalent bond? You see, a covalent bond is a bond that is formed when two atoms share their valence electron with each other. Altogether, when two atoms share valence electron with each other, it forms what we call what? A covalent bond. Altogether. Now, majorly, when this covalent bond occurs, it formulates what we call a molecule. They form a molecule. A molecule. Now, we normally represent the covalent bond with a dash. For example, hydrogen molecule, oxygen molecule, we normally represent them as what? H-H, O-O. Altogether, we can also have HCl, which can be represented as H-Cl. Altogether, we have nitrogen N. Now, this is triple. We can also have carbon monoxide O. Altogether, I think I have a question about this. We are coming back to their own polarity and what's this thing also. So we can have something of this C double bond O. All these that I'm seeing here, they are all molecule. Because of all this dash what in between them, they are what molecule. They are all bonded together with what? Covalent bond. Take note of that. Now, this covalent bond that we are seeing here, it is of two types. We have what we call the polar covalent bond. The polar covalent bond. And then we have the non-polar covalent bond. Altogether, for polar covalent bond, the electronegativity difference of the polar covalent bond should be less than 0.5. The electronegativity difference should be less than 0.5. While a non-polar covalent bond has an electronegativity difference of equals to 0. This is a non-polar covalent bond. The electronegativity difference must be 0. I think I have explained the polarity for you. Now, what you need to understand about this? Are you getting what I'm saying now? Look what I said, it requires a sharing of electron. But before I move on to this in full, let me explain what we call the Lewis structure. Now, the Lewis structure was introduced by a scientist which is known as what? G.N. Lewis. This structure can be used to detect what? To explain the bonding that is found between molecules. We can use Lewis structure to what? Explain what the bonding. Now, what is this structure talking about? According to Lewis, he arranged the valence electron of every atom using a dot or cross method around the atom. So it only uses the valence electron it uses the valence electron of every atom. Now, let me show you something about Lewis structure. I can write the Lewis structure of any atom if I know their valence electron, like nitrogen, for instance. Nitrogen is having an electron configuration of 1s2, 2s2, and 2p. I think that's the atomic number 7, and 2p5, which makes it to be equals to 2x2, then 2p5, which is 2, 4. Supposed to be atomic number 7. This should be what? 3. So that is 2 plus 2, 4 plus 3. That's what? 7. Now, one thing I want you to know, what is my valence electron? Valence electron is the electron that is found in the last shell of the atom. Are you getting me? Or let me say it is found in the valence shell. So this is the valence shell here. Look at this. This is the last shell. Why do we call this shell a valence shell? This is shell 2. Now, total number of electrons that should be there is S should be taken 2 and P should be taken what? 6. But in this case, X is taken 2, but P is taken 3, which is not complete. It makes this whole shell to be incomplete. So we call this whole shell a valence shell. So, according to Lewis, he said we can easily write this valence shell as what? As an electron around the atom. So, in this case here now, the valence electron of nitrogen should be 2 plus 3, which is 5. That is the last listing. Valence electron of nitrogen is equals to 5. Now, how do we now arrange it? How does Lewis arrange this valence electron around the atom? The arrangement is done using Ohm's rule. It is done with what? Using Ohm's rule. Let me now explain what we call Ohm's rule for you. According to Ohms stated a law. He said, electron should be filled into a degenerate orbital singly before pairing occur. Altogether. Now, in periodic table, according to electron configuration, Degenerate orbitals are orbitals that can be split into what? Different magnetic axes. Now, and these degenerate orbitals are the p orbital, the d orbital, and the f orbital. These are degenerate orbitals. P has what? 3 degeneracy, D has 5 degeneracy, and F has 7 degenerate orbitals that can be split into. Now, forget about the D and the what? F. Altogether, let me explain that about the P to write electronic configuration using Lewis structure. Now, if I want to write electronic configuration of this nitrogen that has 7 electrons, it can be done in this place here. I'll be having this 1s2, 2s2, 2p6, sorry, what am I doing? 1s2, this one is 2s2, and then this one should be what? 2p. Sorry, 1s, 2s, and what? 2p. Now let's fill in the electron. You know it has 1s, 2s, and 2p. Let's fill in the electron. According to On's rule does not have any business with all this. It only has a business with the p orbital, which is degenerate. So s orbital can only take 2 electrons. Give the 2 electrons out of 7 to s. Out of 7 electrons, I'm going to fill in s orbital to be complete. It doesn't have any business with On's rule. So this one was having a spin 2, 1, 2. I mean, remaining 5 electrons. I think the next s orbital is also having 2 electrons. Give it 1, 2. Then my problem now goes to the what? The p orbital. Altogether, the p orbital has 3 electrons, but according to degenerate, you need to what? Fill it singly before pairing occur. I should be having 1, 1, 1. That's one by singly. If there is leftover electron, then I will now start pairing. Altogether, so this is the electronic configuration of nitrogen using Ohm's rule. Altogether, now let me explain this electron that is here for you. You see all these electrons that is here that are paired up. These are paired up electrons. Hope you hear me like that. All these electrons here that what? They are paired up. We call these electrons that are paired up, we call them what? Paired electrons. While all these ones are known as what? Unpaired electrons. But my question they normally ask us is, they ask a question one here about the lone pair of electron, and then the lone pair electron and the bonding pair electron. What is the difference between a lone pair and a bonding pair electron? I want you to what? Take note of this. The lone pair electron and the bonding pair electron. Now, we normally have a lone pair and bonding pair in the valence shell. Are you getting me? Now, my valence shell now is this. This shell is not complete. That's what we call it, a valence shell. But just because it's not complete doesn't mean that one of the orbital is not complete. This s orbital is complete with electron of 2. But it is only the p orbital that is having a reduction of 3 electrons. Altogether, now, all these things make up what? An incomplete shell. But in this incomplete shell, this s orbital that is complete, which is this here, is known as a lone pair. It's going to form what we call what? A lone pair. Why? It is complete. But no any atom will bonded to it. Are you getting? No any atom will what? Bonded to it, because it has already taken 2 electrons. So because it is taking 2 electrons, it is serving as a lone pair electron. Lone pair electron. Altogether, now you don't see all this one here can simply accept 1 electron, 1 electron, 1 electron. These ones are known as bonding pair electron. Bonding pair. So bonding pair electron are electrons that can, they are orbitals that can easily accept electrons. Let me say they are electrons that can accept one electron to themselves. We call them bonding pair. This is lone pair. So according to Lewis, I can write this nitrogen to have something of this kind. You further write the lone pair of electron, which is 2 first. You know it has what? 5 electrons. I have the lone pair electron to be 1, 2. Now, another bonding pair electron you have 1, 1, 1. I mean, put it beside it 1, 1, 1. So, if nitrogen is to form a compound, it needed 3 electrons, 3 atoms that has 1 electron each. For example, for you to form a compound with hydrogen, hydrogen is having 1 electron. So, if hydrogen comes, hydrogen will share its one of the electrons here to form here. Another hydrogen will share an electron here to be this. Another hydrogen will share an electron here to be what? This. This form what we call what? Ammonia. Are you getting me? Now, if I ask you, what is the center atom here? The center atom here is nitrogen. Nitrogen is the center atom. And the center atom is the atom carrying the lone pair. Now, how many lone pair do we have in nitrogen? One lone pair. Nitrogen only contains one lone pair of electron and 3 bonding pair. All together with me like that. I think I'm good with this. Let me show you one of oxygen. The one of oxygen, then we can move on. I think this thing is kind of what? Cumbersome. Oxygen is having 8 electrons. Now, if oxygen is having 8 electrons, I should be having electron configuration of oxygen 1s2, 2x2, 2p6. Sorry. For it to be 2, 4. I think here should be 4. 2p4. Yeah. Now, writing the electron configuration of oxygen using Ohm's rule, I will now be having, so that we can form the Lewis structure, I'll be having 1x, 2x, then I should be having, this is 2p, which is degenerate. So, according to my explanation, 1x should be filled with its own 2 electrons. Remove 2 from this 8 electron, fill it to 1x, 1, 2. I don't have any business with this first orbital. My business is going to the what? Second orbital. Because even though Lewis structure is only talking about the second and the last valence shell, but I just need to just explain how this thing is being filled for you. So I have 6 electrons left, give it 2, and then this one should be what? Remaining 4 electrons, then share it singly first, 1, 1, 1, then start pairing 1. Now, my question is, how many lone pair do oxygen have? How many lone pair will what oxygen have? I want you to what? Give me an answer. Just check yourself and what find answer to me to that. Let me just give you some seconds. Now, let's continue. Now, in this case, don't forget I said I'm only considering the valence shell. The valence shell of oxygen is this. This is the valence shell too. It has 6 electrons in its valence shell. But among that 6 electrons, 2 of the electrons, so this one is paired up, Abi. So this one is a paired electron, This is unpaired, all together. So these 2 unpaired electrons should formulate what we call the bonding pair. The bonding pair electron. Why this one and this one will formulate? Because this one is paired, this is known as the lone pair. So oxygen has how many lone pair? It has 2 lone pair and 2 bonding pair. How do we write that in oxygen? Using Lewis structure, I should be having it like this. 1, 2, 1, 2. Since I lone pair, then 1, 1. So these 2 are the bonding pair. These 2 are the what? Lone pair. So oxygen can react with hydrogen with this, all together. So I think this thing, I'm coming to explain to you how this thing affects the geometry of oxygen and how this lone pair affected the geometry, the shape of oxygen, the shape of this molecule, water molecule, and how it affected the shape of what? Ammonia. All together. I think I'm good with that. Are we there? So that is that for that. So let's move on to what we call what? I said we have polar covalent bond and non-polar covalent bond. For polar covalent bond, the electronic configuration must be less than 0.5 or less than or equal to. Then for non-polar covalent bond, the electronic configuration must be what? The electronegativity difference must be equal to 0. Now we can find this one. Polar covalent bond is a bond that exists between what? Elements of different atoms. Atoms of different kind. Atoms of different kind. Like hydrogen with chlorine, carbon with oxygen reacted. This one form HCl. This one form what? CO2. Or nitrogen with hydrogen to form NH3. All together, phosphorus with chlorine to form what? PCl3. Boron with fluorine to form what? Boron fluoride. Are you getting something now? All these, beryllium with chlorine to form what? Beryllium chloride. Are you getting this? Beryllium what? Chloride molecule. Now, all this that is here, methane, CH4, CCl4, tetrachloro what? Methane. All these are molecules that are polar. They are polar covalent bonds. Please take note. I'm not saying anything about molecule for now. They are known as polar covalent bond. Again, they have a polar covalent bond. According to the definition, the polar covalent bond is the bond that exists between molecules. Between what? Atoms of different kind. Like all this, they are different kind. Now in this one here, their change in electronegativity value is less than or equals to 0.5. So they form a polar covalent bond. All together. Now, the next one is what we call what? The non-polar covalent bond. The non-polar covalent bond exists between molecules of this, between atoms of the same kind, and that will be forming all these noble gases structure like hydrogen and hydrogen, okay, to form H2, oxygen gas, nitrogen gas, I think Cl2, chloride molecule, all together, fluoride molecule. All this that is here are having what we call non-polar covalent bond. I'm not talking about the molecule now, because there are some time in which the molecules, the bond might be polar while the molecule is non-polar. I'm going to explain that in another video for you. All together with me like that. So this is having a non-polar covalent bond. Now let me take a look at the question on it, so I can move on again with another interesting things about this. Now, I think I have a question here. Okay, they said the electronic configuration of elements X and Y are the electronic configuration of elements X and Y. We have 2, 8, 6. This is element X. Element Y, the electronic configuration is 2, 8, 7. Element Y. The bond in the compound formed by X and Y is expected to be what? Now take note, how do we understand the kind of bond? Now, this is the valence electron. This is the what? Valence electron, because this one is already complete octets. So, if you want to know the bond that exhibits, this kind of question is very, very simple. If the valence electron is between 1, 2, are you getting what I'm saying now? If the valence electron of one of the atom is 1 and 2, and this one is now like 6 and 7, then the bonding between them will be what? Electrovalence. But if the valence electron is like 6, 7, look at the valence electron between both of them, 6 and 7, this is showcasing that both of them, they are non-metals. Non-metals. It's only because this valence electron indicates their group number. This showcases the elements in group 6. This showcases elements in group 7. So if I have valence electron of 5, elements in group 5, and look what I said, whenever from group 4 to group 7, they are all non-metal. So if you have a valence electron of 4 to 7, know that they are non-metal. And the bonding that exists between two non-metal is known as covalent bond. Covalent bond. So this is non-metal. The bond between them will be what? Covalent bond. That's the option. Option A, we have ionic bond. Option B, covalent bond. Option C, Dextric covalent bond. Option D, metallic bond. And then E, none of the above. We are coming back to metallic bond. Okay. Okay, an element with atomic number 12 is likely to be an element with atomic number 12 is likely to be A, electrovalent with a valency of 1, B, electrovalent with a valency of 2, covalent with a valency of 2, and then covalent with a valency of 4. Atomic number of the element is 12. If you want to know the answer to that, the only thing you can do is that what? The element is having atomic number 12. Then you write the electronic configuration of the element to be equal to what? 2. Using shell method, 2 is complete. Remove 8 again. 2, 8. How many electrons is left? I think I have, this is 10. I made 2 electrons, put it there. 2, 8, 2. I get me. Don't forget I said when the valence electron is 1 and 2, then that element will be undergoing what kind of what? Bonding, electrovalence. All together. Now, this is the valence electron of 2. So let's take a look at, let's pick our option. An element with atomic number 12 is likely to be what? A, electrovalent with a valency of 1. No. It is electrovalence. Well, because it has what? 2 electrons. But it can make it be 3, 4, 5. It is changing. Altogether. So it is electrovalent with a valency of 2. Electrovalent with a valency of 2. So answer should be what? B. An element with this is what? Electrovalent with the valency of 2. I think that is good for that. Now, let me now take a look at this, the property of these elements. What is the property of the covalent bond that we need to know? Now, one of the major properties, these are the properties of covalent bond. Number 1, they have what? They are low melting solid. Low melting solid. Low melting solid. Solid. And then number 2, they are what? Okay. They have low boiling. Low boiling what? Liquid. Low boiling liquid. I get something now. And what? a volatile what? Sorry, they are volatile. They are volatile. Okay. Number 3 is that they does not conduct electricity. They do not conduct electricity. Are you getting me? Number 4, they dissolve, as in the polar ones. Polar ones among them dissolve in water. Are you getting what I'm saying? And also dissolve the polar ones. The polar covalents dissolve in water and in a non-polar solvent like benzene. All together like that. And number 5 is that what? They have a slow reaction. They have a slow reaction. That is, I want you to know all this. All together, that's the property that might ask for you. Let me check the question on this property so that we can what? Move on. The property of chlorine, which causes hydrogen chloride to be more ionic than the chlorine molecule, is its A. Electronegativity, B. Electropositivity, C. Electron affinity, and D. Electrovalency. The answer should be electronegativity, which is A. It is because of the electronegativity of chlorine, that is why hydrogen chloride is more ionic than chlorine molecule. Because of the electronegativity of chlorine, which is higher than the electronegativity of hydrogen. So in that molecule, hydrogen, if they are both sharing, if hydrogen is sharing electron with what? Chlorine, don't forget that this one should be 1, 2, 1, 2, 1, 2. According to Lewis structure, 1, then 1. All together. So this one donates 1. I think there's one that I forgot to explain. In covalent bonding, the two elements are, the two atoms are donating shared electron. One share, and they are donating what? Shared electron. In this case, between hydrogen and chlorine, hydrogen donates 1 shared electron, and what? Chlorine donates 1 of the shared electron. But the problem here is that chlorine is highly electronegative than hydrogen. That's one of the properties that make this thing to be ionic. Because of the high electronegativity of chlorine, chlorine tends to draw the electron towards itself altogether in the compound, and if you leaving hydrogen to be what? Having no electron, then hydrogen will now be having a what? A partial positive, chlorine will be having a partial negative, which makes it to be polar molecule. So hydrogen chloride will dissolve in water. Why? Because of this partial polarity that it has altogether. So my answer to that question is because of what? The electronegativity of chlorine. In anything about bonding, if you are talking about bonding, we talk about electronegativity of one of the elements mostly altogether. So thank you for watching this video. In my next video, I'm going to be taking a look at the coordinate covalent bonding, and then I'm going to be taking a look at polar molecules. Why are some substances having covalent bonding, but these substances does not dissolve in water? And we're going to be taking a look at what? Metallic bonding as well. Thank you so much. Please don't forget to click on that subscribe button that is found below, and also share my video with your friends. If anything that you are disturbed about that you don't really understand about this topic, drop a comment for me in the comment box section below. I'm going to be explaining everything to you in due time. Thanks so much.